Okay, so in the previous video, we defined the q-polynomials by this formula. So n over m in the square bracket as 1 minus q to the n times 1 minus q to the n minus 1 all the way to 1 minus q to the n minus m plus 1 divided by 1 minus q to the m, 1 minus q to the m minus 1, all the way down to 1 minus q. So that's how we define this. And we would like now to discuss the combinatorial nature of this. So here, the understanding is that n is greater than or equal to m. So to look at the combinatorial nature of this, we might want to rewrite this as m plus k over m. So we actually replace n by m plus k, and here we suppose that actually for our purposes, we will use that n is greater than m, and m is and k is greater than or equal to 1 in this setup. So so here's what we do. We consider a rectangle that has dimensions m and k. So let's say that it has m rows, and that it has k columns. And we ask the question of how many partitions in general fit in this rectangle. And we want to think of a partition in terms of its Young diagram. So you see that there's indeed a restriction on both the numbers that we have in the partition. So we can have partitions in at most m numbers. Of numbers less than or equal to k. So the numbers that you can use in these partitions cannot exceed k, and you cannot have more than m of them. So for example, to give an idea of what is going on here, let's say that I'm singling out this particular Young diagram as a simple example. This one right here, just to make it a little more obvious, let me just shade the squares that So in this diagram, I have 3 numbers, and none of them exceeds, well, in this picture, it's 10. So it's a partition 6, 4, and 1. So it's it's a partition of the number 11. Sometimes if I write this this way, then I write that the size of the partition is 11. So the number that is being partitioned is 11. And here the important thing that one should consider is that such a Young diagram corresponds automatically, oops, sorry about this. So such a Young diagram corresponds automatically to a path that goes from the lower left corner to the upper right corner and just goes on the edge of this diagram. So you begin right here, you go up, then to the right, then up, to the right, to the right, to the right, then up, to the right, to the right, up, and then 4 places to the right. And I claim that as long as you have such a path, that describes a diagram and vice versa. So there's one-to-one correspondence between Young diagrams of with no more than m rows, each of which has length less than or equal to k, and paths in a grid of m times k squares that originate at the lower left corner and use steps either up or right to reach the upper right corner. Okay, so there is one-to-one correspondence, and the reason that I'm mentioning this is because it's not too hard to actually count the latter, which means that we can count how many such diagrams we have altogether. And how do we do that? Well, if you think about it, the number of steps that you need in order to go from the lower left corner to the upper right corner, so number of steps, oops, sorry again. So number of steps that are needed, either upper steps or steps to the right. So number of steps is, you pretty much need always m steps that go up and k steps that go to the right. So it's m plus k. And in order to make such a path, you just have to choose the places where you're going to insert the steps that go up, for example, and there are m of them. So if out of the m plus k steps, you designate which steps should go up, such a path is determined by the number of steps that are going up, and that's m. So it depends on how you're going to distribute these steps. And this number is, of course, m plus k over m, which is precisely the number of Young diagrams that fit in this grid. So that's same as number of Young diagrams that fit in this grid. So the other thing that we can ask is, the Young diagrams that fit in this grid can represent partitions of what numbers? And pretty much you can have partitions of 0 if you consider a trivial Young diagram that really has no rows or no columns, all the way to k times m, which is if you have a Young diagram that has all the rows of length k. So the partitions vary from partitions of 0 all the way to partitions of m times k. So we can ask here for each number between these two numbers, 0 and mk, how many such partitions we get. So if we denote this number by pmk of n, so this is the number of partitions of n into at most m numbers that do not exceed k, then we can consider, in the spirit of the number of partitions that of the Q series that we talked about in Euler's solution of the partition problem, then we could consider the polynomial starting from n equals 0 to mk of p of mk of n times q to the n. So this would be the same as saying what partitions fit inside the grid with m rows and k columns, and we just add up q to the size of the partition. So that would be precisely the same thing. So our contention here, and this is where we like to make the connection, is that it turns out that this polynomial is precisely m plus k over m. Okay, so it turns out that this is precisely the case. And what we would like to do is pretty much justify why this is true. But for the moment being, all we wanted to do is identify these polynomials as polynomials that are linked to partitions where we control both the number of terms in the partition and the size of terms in the partition. And that's all. Thanks for watching.